Okay, I'm Scott Parker from the Argonne Leadership Computing Facility, and I'm going to be talking about performance tools that we have on our BlueGene systems, Mira and Vesta. I only have 20 minutes, so I'm going to try to keep this short and sweet. So these are the tools that we have on Mira and Vesta. So is that too short? Should I go into more? As you can see, we have quite a few. We have almost a dozen, and this is due to a lot of hard work by a lot of groups, people at Argonne and other groups here. So we have John Mellor-Crummy, who's going to be talking later about Rice HPC Toolkit. He did a lot of work with IBM to make his tool work well on the BlueGene system. And we have Al Maloney here from Tau. He'll be speaking later too about Tau. Both these groups have been involved in the BlueGene since before there was a BlueGene and getting their tools ready. And they'll be talking about more of these tools more later, so I won't talk too much about them. Since I'm sort of kicking off a session that starts, or an afternoon that starts covering performance tools and debuggers, I want to do two things. One is talk about the performance tools that we have on our system, but I also want to kind of give you a little bit of introduction to what performance tools are and why you would want to use them. So you've written a code, you've got it on the machine, you run it, and it gives the right answer. This is great, right? So you're all happy, you've got your answer. But then you realize it's going to take 2 months to do the simulation. That's going to be your thesis, and you only have 1 month of computing time. So now you're not so happy. So how do you figure out how to make it go faster? Or maybe you have a code that runs great at 128 nodes, but when you run it on 256 nodes, instead of running twice as fast, it runs half as slow. So what's going on? How do you figure that out? Well, just running your code on the machine by itself, usually you don't get a lot of feedback. It's kind of a black box typically, unless you put a lot of instrumentation into your code itself. Performance tools are things that you can basically add on either through libraries or calls to instrumentation libraries that will provide you more feedback about what's going on, how your code is running on the machine. And each machine is different, so your code may do great on one machine and not so great on another machine for various technical reasons. And usually those are architectural specific, and you need some more information to try to understand what's going on. And so that's what these tools do. And I'll talk about the various packages that we have on our system and what they do to give you this information, what kind of implementation they can provide. But I want to emphasize, these are just tools, right? I mean, this is literally, the analogy to tools is very apt in the sense that if you have a toolbox, if you have a problem, with an appliance at home and you have a toolbox, you don't just reach in and grab the first thing that your hand finds, pull out a hammer and start whacking at a bolt, hoping that'll fix the problem, right? Same with performance tools. You really want to pick the right tool for the right job. And we have a variety of them. Some of them do overlapping things, some of them do unique things. And so what I would suggest you do is before you start using any tool is think about which tool you want to use. And I'll cover some of what these tools do so you have some informed, some information to make an informed decision about this. The other thing you want to think about is what information do you want to collect? Where do you think your problem might be? Even if you don't know, if you have a guess. And then you want to look at, the other issue then is how to interpret the information that the tool provides. And that can take some work sometimes. There's a little bit of learning curve. And finally, once you have this information, you're going to want to look at how do I improve my code. And that's a whole other issue unto itself. But the tools will give you a very good start and some very good suggestions. So these are really just tools. They're not going to do this for you, okay? So don't just pick one up and expect it to somehow make your code magically run twice as fast. You really need to use your brain along with the tool to make the improvements to your code. So quickly I want to go through just to kind of give you a little bit of background on what these tools do and how they work. Is different tools collect different type of information. Now the most basic information you get out of a tool is how much time is your code spending in different segments. So usually this is on a function level. So that's often the first thing you want to look at. It's how much, what's the distribution of time for my code. Other things you might want to see is what routines are calling which other routines. If it's a code you haven't written yourself, this can be useful information in just trying to understand the code. And then you can combine these two things to say not just how much time is being spent where, but who's calling who, and when the function A calls function B, how much time is being spent in function B when called from function A. So if you have a matrix multiply, you might call it from multiple locations. And in some cases it goes really fast, and in other cases it goes really slow. So you want to know, where is it being called from, and how much time is it being consuming when it's called that way. Another useful thing, type of information that can be collected is arguments that you pass to subroutines. So you'll see this commonly with MPI. If you make a call to MPI send, you might want to know what's the average message size of my messages on this simulation, or what's the largest message or the smallest message. Some of these tools will be able to intercept your calls to MPI and record the information about the message size that you provide to it. Same thing with I/O. On a more fine-grained level, there's specific hardware details that's unique to each machine, And the way you can gather information about what's going on the really fine-grained hardware level is through hardware performance counters. So hardware performance counters are basically little bits of hardware that are scattered across the machine that count when certain events occur. And so you'll be able to get information like how many floating point operations did you do, or how many bytes did you move from L2 cache to the processor, things like that. And a final thing you might be interested in, especially on the machines these days, is memory usage. I don't have a lot of time, so I'm not going to go through the next few slides in detail, but I do want to mention there's different ways that these tools collect this information. So when you're choosing a tool, you might want to keep in mind how it's getting its information, because that'll give you some sense of how much overhead is the tool going to impose, what are its limitations. So one way it can collect information is just instrumenting your code. Now this may be you going in and manually adding calls to your code, or a tool like Tau can actually take your source code and run it through a parser and add instrumentation for you. Other tools can add instrumentation to the binary. This has pros and cons. It gives you a lot of control, but it also has limitations in the sense that often you can't see what's going on in libraries. If you don't have the source code to something, a lot of tools you can't instrument it then. So if you're calling a math library that's consuming a lot of time, you won't be able to see why. Another approach that can give you more information about that sort of stuff is sampling. So tools like HPC Toolkit do this, where basically they pause your code every so often and look at what it's doing. So this is very analogous to polls, political polls, where they don't ask everybody in the country who they're going to vote for, but they go and ask a subset of people who they're going to vote for, and from that they can construct, oh, Obama's going to win, or Romney's going to win, or something like that. Same idea. With performance tools, they can look at what your code's doing in intervals of time, and based on that sample, they can construct a big picture of where your code is distributing its time. Now, just like political polls, there's margins of error, and this margin of error depends on how many samples you have. So if you have a small sample size, the numbers you get aren't so great. But usually you can get a fairly large number of samples if you run your code long enough, and you can get a very accurate picture of how your code is using time. So another source of performance information that I mentioned before is library interposition. So this is basically just intercepting the calls to various libraries and recording information. So tools like Tau or MPIP or IBM HPCT will do this, and I'll talk about this a little later. And the final source is the hardware performance counters. So like I said, these are little bits of hardware that are added to the chip. So they look at things like there's basically a register that every time a floating point operation occurs, it increments by 1. And you can query these registers and say, how many floating point operations did I do in this section of code? Or how many memory loads or stores did I do? So this can give you a lot of very fine-grained information about what's going on in the machine. Now these vary from machine to machine. The BlueGene Q has over 400 hardware performance counters implemented on it on a chip. So there's quite a bit of information you can pull from them. So this is the first slide that I put up, and I'm just going to come back to it, where if you notice on the far column on the right, I've sort of put some brief annotations about what the tool does. For instance, MPIP collects MPI information through library interception. So this is kind of Cliff's notes to what the tools do and help you kind of narrow down your list of choices when you're going to pick a tool based on what kind of information it collects and how it collects it. And what I want to do now is kind of give you a quick run through of the various tools that we have on the machine, a very brief introduction to how to use them. Mostly, these slides have detailed, notes on how to use them, and I think it'd be useful for reference, so I'm not going to go through all the details in the interest of time here. The first tool I want to talk about is the BGPM API. So this is the API to the hardware performance counters that comes on the BlueGene Q machine. And like I said, basically it lets you see in sort of very low level detail, what the machine's doing, what the hardware activity has looked like when your code is running. The BGPM API is implemented in C, and it's available on the system to collect information from the various hardware counters that we have. So there's quite a few of them distributed across the CPU, the L2 caches, the memory unit, the dev bus, all sorts of bits. And here's a little schematic. And basically, this is just showing you the various bits of, see this L2 core, caches. These are the cores, network, memory units. These all have little counters on them. And these counter information is periodically gathered and centralized into a central counter unit that you can query. This just gives you a little more picture of what's going on one of those units. So this is the processor core itself. The processor core has several what they call functional units. And unfortunately, when you use these tools, it does require some knowledge of the hardware to really make a detailed understanding of what's going on. But it's also a good way to learn about the hardware by looking at what the tools tell you. So on the BlueGene Q chip, for instance, you have a floating point unit, you have an integer unit, you have a load store unit, and they each have counters on them that are counting independently and are configurable. All this information is gathered up and queryable by your program. Now, there's some limitations. On a hardware level, this can get fairly complicated. And so there's some limitations in terms of the combinations and permutations of events that you can collect. But actually using this API is not very hard. I put a little snippet here that sort of shows by example how you can use the BGPM API. And I won't go through this step by step, but what I want to point out is there's basically about 8 calls here that you have to make. And essentially, it's initialize the counters, tell it what you want to count, apply the counters to the hardware, start them, stop them, read them. So it's really not too hard to use. If anybody's interested, this is on our system. It's installed in this directory, and there's a sort of convenience link to that library here, because all of our tools live in the soft perf tools directory. So if you ever wonder where is a tool on the BlueJean queue, look in the soft perf tools, and you'll find it there if we have it. There's documentation on our website on all of our tools. So if you have any questions about how any of our tools work, just go to the ALCF website. It should be under user guides, and then you'll find a series of these things like BGQ, performance counters, PAPI, TAO, HPC toolkit. IBM actually, we complained about the BGP documentation for our hardware performance counters, and they did a great job documenting the BlueJean Q hardware performance counters, comparatively, I should say. I see John giving me questionable looks right now, but I think compared to where we came from, they've improved it dramatically, let me put it that way. This is HTML documentation, and it's in the system directory there that's also accessible through soft perf tools. And if you're interested in it, I encourage you to take a look. One of the things that it has that's very useful is a list of all the things you can get from the hardware. So there's pages and pages of these that show you all the various hardware events that you can query the system about. So you can find out basically everything that the hardware is doing with your code. Now, this API is specific to the BlueJean Q. So you may think, well, I want to get this information about the hardware performance counters, but I really don't want to put all this BGPM calls into my code because I'm going to go and run it on Titan or some other system next month or next year. Well, so instead of using the BGPM API, there's another API called PAPI, where other people have had the same problem, decided, well, why don't we make an abstract API that can let us query the performance counters on any system that's supported, and they support the BlueJean Q. So we have PAPI installed in Soft Perf Tools PAPI, documentation on the PAPI site and on our site, and it's very similar. It looks very similar to the BGPM API. In fact, they modeled the BGPM API after PAPI. So it provides a really simple interface that's literally like 4 calls that will get you some very useful information from the hardware performance counters. But if you want to delve in, you can use the higher level or the lower level interface and get almost as much detail as you can get from the BGPM API. There's various events that they've defined, and there's in the documentation they'll show you how to run it. But there's a tool called PAPI Avail. If you run that on the compute nodes, you have to run it as a batch job. And this is in Soft Perf Tools PAPI bin. If you run that, it'll spit out a list of everything PAPI, all the events that PAPI can provide you information on. And I apologize if I'm going through this fast, but since we don't have a lot of time. These slides are here for reference. We also have documentation on our website, and I'll be around today and this evening, so if people have questions, feel free to follow up with me. Another tool that we've had at the ALCF for a long time now, we've worked closely with, is TAO. Al Maloney is here, and he's going to speak later about TAO, so I'm going to kind of skip through this, and I'm just going to point out that TAO has a lot of functionality and features. It can collect information on both timing, MPI usage, hardware performance events, pthread, OpenMP usage, memory usage. This is installed in Soft Perf Tools TAO. There's documentation again on our site, as usual, and on the TAO site. Another tool that we've been using for quite a while and has worked with a lot is the Rice HPC Toolkit. That's from John Miller-Crummy, who's going to be speaking later. And this is a sampling-based tool. So this tool it takes a different approach than a number of the other tools, and I think they pioneered some of the advanced use of sampling with the HPC Toolkit. And it'll give you a lot of information about not just how time is being spent, but also how other hardware events are distributed throughout your code. John's going to be talking about this, so I'll just leave it at that and say that it's installed on our system in the usual place, Soft Perf Tools, documented both on our site and on the Rice HPC Toolkit site. Now, both TAO and HPC Toolkit are fairly, I want to say complex, but they can gather a lot of information about your code, and they can give you a lot of insight into what's going on in many different ways. Sometimes if you want to do something short and sweet, maybe not get as much information, but maybe not have to learn quite as much to use the tool. There's simpler things that are libraries that you can just link into your code. One of them is IBM HPC Toolkit. It can provide you information on both the MPI usage of your code and the hardware performance counters. So it's basically a collection of libraries. So there's 4 libraries here that you can use. One is MPI Trace, one is MPI HPM, and there's 2 others for threaded code. I have 1 or 2 slides here about how to use this, and it's fairly simple, but before I get to those, I just want to say, again, this is installed in the usual place and documented in the usual place. So MPI Trace basically will collect information about how your code uses MPI. This is the only thing that it does. It doesn't do anything else. It won't tell you how your matrix multiply is performing or anything like that, but it'll tell you how your send, receives, broadcasts, all reduce, that kind of stuff is using time and how many bytes are being sent back and forth. It gives you the option of basically localizing the data collection through very few. These are basically the only API calls that that it has. So it basically gives you a start and stop if you want. You don't have to use these. It's actually started by default when you link in the library. And this is how you use it. Essentially, you don't have to do anything except add the library to your link line. So you basically just add the path to the library and then the particular library that you want to use. So once you've done that, you can just run your code as usual. And after you've run your code, you should see a couple of these MPI profile.rank files. Typically, there's 4 of them. One with information from rank 0, one with information from the rank with maximum time, MPI time, minimum, and average MPI time. And this may not seem like a lot. You're getting information from 4 ranks, and let's say you ran with 16,000 ranks. But it's actually quite insightful. I mean, it's a very limited amount of data, so tools like HPC Toolkit or Tau can give you a lot more. But this is a very concise, I guess, summary of what's going on with your code. And so it can give you simple information like this, how much time was being spent in MPI send, how many bytes were sent, that sort of thing. Similarly, there's another library called HPM, and that does for hardware performance counters what MPI Trace does for MPI. So basically, it's just a library that you link in. It's got 2 API calls that if you want to use them, you can do that to control when it's running, so you can turn it on and off. But otherwise, you basically just link in the library. There's an example of doing this in C and Fortran into your code when you compile, and then you run your code. And after you've run it, you should see 4 files again. In this case, the files are HPM summary. They'll be from the same ranks that you had the MPI information. And it basically gives you just a little summary of how the hardware performance counters are being used. So you can get things like floating point operations performed, L2 cache misses, things like that. There's another library on the system called MPIP, and really this is almost completely redundant with MPI Trace. It's there basically as a convenience for people that have used MPIP on other systems and are comfortable reading its output. I wouldn't recommend it. It's probably not been used as extensively on our system as MPI Trace, but if it's something you've used before and you like it, it's there. You can give it a try. I've used it a little bit, so it does work, but I haven't tried using it at large scale. I have no reason to believe that it wouldn't work at large scale, but some of these tools have had more extensive testing than others. And this tool, like MPI Trace, is fairly straightforward. You just have to link it in. There's a few additional libraries you have to add, but if you just add these libraries on your link line, then you can just run your code, and you'll get, in this case, 1 file out, a single .mpip file that will contain all the information about how your code's using MPI. A sort of tried and true tool that's on our system is gprof. It's probably the most widespread performance tool out there. If you have a Mac laptop, which I see a number of you do, you actually have gprof on there. So it's basically an open source tool that's in most all Linux distributions, as far as I know. It's not the best tool to use, I would say. It's not going to give you the most information, but like I said, it's widespread. So if you've used it, it's on our system. It also takes a sampling approach on data collection. And so it'll give you basic information about how much time is being spent in various routines of your code, and you can also get call graph information from it. Using it is probably the least difficult of any tool, with one exception at the end here, which is you just add -pg-g to your compile and link lines, and once you've done that, you'll get a executable that you can run on the system. And on our system, one wrinkle or feature of gprof is that by default, if you run with, say, on our system, you could run with up to 1.5 million MPI ranks. gprof is going to want to produce one file for each MPI rank, which means you would get 1.5 million files, which would make our file system very, very unhappy, as well as our administrators and a number of other people. So you'll probably get some nasty emails from them if you do this. So what they did by default is tone it down so that it only produces output from the first 32 ranks. Now, if you want to see more, you can set an environment variable here that basically lets you say the max, min, and stride for the ranks that you want to see. So you could say, starting at rank 1,000, going up to 10,000, give me the output from every 500th rank. So you'll get 20 some odd files from that. And once you've got the output files, you use gprof to view them. Briefly, I just want to mention that we have Scalasca on our system. Scalasca is a tool that's developed over in Jülich in Germany. We've used it a bit. They have a BlueGene queue over there, so I'm reasonably confident that it works well on our system for a variety of codes. I would refer you, if you're interested in Scalasca, I would say go ahead and try it. It's not as widely used on our system, so we don't have as much experience with it. Tau and HPC Toolkit are probably the primary ones that people use, but if it's something you've used or are interested in playing with, go ahead. And similarly, we have a tool called SpeedShop. Again, this is more of an experimental tool on the BlueGene queue. It hasn't been used as extensively on our system as some of the other tools, but if it's something you've used somewhere else, it is installed. Again, usual place, soft perf tools, so you're welcome to give it a try. And finally, this is actually the simplest tool to use that we have on our system. It's for collecting information about how your code uses I/O. It's called Darshan, and it's actually enabled by default. So every job you've run so far on our system, Darshan has been there in the background collecting I/O information. And if you want to see this information, you can go to this directory, /gpfs. Now, in this case, I'm pointing to the Mira directory, but if you're on Vesta, just replace every mention of Mira here with Vesta. If you go and look in that directory, you'll actually find data that's been gathered by your code. And there's a little viewer that you can use to output that information, and it's documented, discussed in our user guide here on Darshan. So if you have any problems with I/O or questions about I/O, Darshan is there, and it's already collected information about what your code's doing with I/O, and you can take a look at it. OK, so this is my second to last slide. And this is really a very crude summary of what I would suggest. If you're not sure what to do as far as using performance tools, this is kind of my most basic roadmap as to how you might want to proceed, which is first, if you have no idea what your code's doing or how it's performing, go ahead and use a tool to look at where it's spending its time, because that's really the thing that you want to look at is routines that are consuming a lot of time. Those are the ones you want to give your attention to. So Rice HPC Toolkit, Tau, gprof are all good tools for getting a good overview of how your code is distributing its time amongst the functions in it. If you know that my problem is in MPI, I know that my code's not scaling well and it's because I'm doing something with MPI badly, but I'm not sure what, then you might want to gather information about how your code is using MPI. So tools like the MPI profiling library and the IBM HPC Toolkit is useful. Tau can get that information, or MPIP can get that information for you. And finally, if you've narrowed it down and say, OK, this function is consuming a lot of time. I don't know why. Something's going on. It's just running very slowly on the processor. Then you're going to have to look at You're going to have to look at what's going on in the hardware, and that information is going to come from the hardware performance counters. So that's going to tell you things like how many cache misses you had, what's your floating point rate, what's your instruction issue rate. So if you really have narrowed it down to this routine is doing badly, then you can start looking at the hardware performance counters to understand what's going on in fine-grained detail in that routine. And the last slide I have here is really just a pointer to a test code that I have. This test code doesn't do anything really physical. It's really just a collection of kernels. So matrix multiplies, matrix vector multiplies, some streaming vector updates, and it's also got some communication in it with point-to-point, all reduce and broadcast. And it's got OpenMP in it, too, that you can turn on and off. So this code is in my home directory on Vesta, home, Sparker, temp, ATPESC. If you just copy that directory, you'll get this test code. And one of the things I did with this is I instrumented it myself with just some timers. So if you put this -d, there's a make file there. So if you do make all, it'll make 4 versions of it, one with OpenMP and one without, and then one with the internal timers on and one without. And the internal timers will tell you in detail how much time each routine's taking, and it'll also provide information about the broadcasts, all reduce and MPI send receives, message size and stuff like that. So you can run this with the timers, the instrumentation, the internal instrumentation on, and it's a fairly small code. It makes like a dozen calls. It's easy to understand what it does. And then you can look at that information, and then I find this helpful if you're using a tool for this first time. Take something that you understand how it runs, and then fire up the tool and use the, that simple code as a reference to interpreting the tool's output. And there's a little brief description. I mean, it's fairly small code, so if you look at main.c, it should be fairly straightforward to understand. Okay, I think my time is up, but I'll close with any questions people might have. Yeah, you can tune it too. You can set the number of loop iterations. So if you want, you can, at the very top, there's a bunch of defines, and so you can say how many loop iterations, so you can run it for a second or 2 hours. And you can change the distribution of time between all the different parts by changing their sizes. So you could have it spend all its time in matrix multiply and no time communicating. So, any other questions?
So Scott will be around the whole day.
Okay, I think we had one quick question.
Quick.
Okay, so the question is, if you're running on a large part of the machine, what kind of overhead would they have on the running application? I will say that depends a lot on what your code does and how the tool collects information. Some tools can impose a significant amount of overhead, particularly if you have cases where you go in and out of a lot of functions, very short functions that you go in and out of many, many times. Now, tools that do sampling typically can have less overhead. So HPC Toolkit, I think, John, you typically see what, like 1 or 2%? Couple percent. If you're seeing more than that, especially if you're seeing more than 5 or 10%, you definitely talk to us, and we'll try to find a tool that, because you run into the danger of distorting your run, your runtime, the information you're collecting if your tool is causing problems and imposing overhead. But in most cases, you shouldn't have significant overhead. At least we can find a tool that won't impose it for your code. Okay, I think my time's up, but I'll be around if anybody has questions.